and I correct the slide, so the name of the university is not correct in the first slide. In this talk, I will talk about one of my recent works, which is an improvement of a recent paper of David Aldous on a problem on random binary trees. I will start by the history of the problem and the model, and then I will explain the contribution of Aldous, and then my contribution to improve the bound provided by Aldous. The model that we have, the objects that we deal with are binary trees. By a binary tree with leaf set A, I mean a tree such that the leaf set is A, and every other vertex has degree 3. So the degree of vertices are 3 or 1. Here, the leaves are important for us, and the branch points are not important. Equivalently, we can have we can look at the leaf set as labels on the vertices. So there are two different views of thinking about it. For example, we can assume the tree drawn on the plane, and we put labels 1 to n on the leaves. These trees appear naturally in biology, for example, in phylogenetic trees. This picture here shows the tree of life, which is the family tree of all animals and plants and other species. It shows how they have branched in the history from a single species, which is in the middle, and because of the mutations, other kinds of species have been created. As we see here, these leaves correspond to the different species, but the branch points do not correspond to a species. They just show the combinatorial structure of the tree.
Just a quick question, please, Dr. Ali. The label of the leaves are the first leaf is labeled 1. It's okay or not? The first leaf 1 is for the first leaf. The label 1.
The first leaf.
The first is labeled 1, and the second label 2, and so on.
Yes.
Okay.
So we have a set of leaves, which here we assume there are n leaves, and on each leaf we have written a number, a unique number, and the numbers are from 1 to n exactly. Each number appears once exactly. So we have the same tree, but with another numbering of the leaves. So these two are different for us.
Okay.
In the left-hand side in this picture, I have drawn two different trees with 12 leaves. This picture is from Aldous's paper. And on the right, we see a subset of the leaves, which is 3, 6, 11, 4, 9. If we look at this subset on the big tree, we can join every two of these leaves. We see a red graph, which looks like this. And if we delete the intermediate vertices, like the one here, which is a vertex of degree 2 in the red graph, but if we delete them, we can look the result as a binary tree as well. So in the left-hand side, we obtain a binary tree, which is induced on the subset of the leaves. Here, this one is not a branch point here. It just determines an edge. So if we have a subset of the leaf set, we obtain an induced subtree. I have done the same in the lower tree. This shows the induced subtree on the same subset of leaves. And if we think a little and compare these two trees on the right, we see that they are isomorphic, which means that if we permute the leaves, we obtain the bottom tree from the upper tree. Since these two trees are isomorphic, we say that we have found a common subtree of the two big trees. This common subtree is a measure of similarity of the two trees. For example, assume two people have drawn two trees of life, but they are not exactly similar. There is some difference between the two trees. The larger the common subtree is, we say that the trees are more similar. So this largest common subtree measures the similarity of two trees. Here is a more formal mathematical description. Assume that we have two trees, T and T prime, with the same leaf set, and A is the set of leaves. We say that these two trees are isomorphic if there exists a graph isomorphism which preserves the leaf labels. But the branch points do not have labels, so nothing is needed to be preserved. Just we need that every branch point is mapped to another branch point. But on the leaves, we require that the leaf of vertex 1, the leaf of label 1 should be mapped to the leaf of label 1 in the other 3. We say that a common subtree of T and T prime is a subset of the leaf set such that the induced trees on the subset are isomorphic, as we saw in the picture. We call kappa of T and T prime the size of the largest common subtree. Here, by size, I mean the number of leaves, because only leaves are important for us. We count the number of leaves of the common subtree, and we say this is the size of the tree. And this kappa is a measure of similarity of the two trees. We want to study the asymptotics of this kappa for large trees. There are various problems that we can ask. For example, we can ask about worst case scenarios where T and T prime can be any binary tree. So the question is, what is the minimum of kappa among all binary trees? It is not hard to show that this is of order logarithm of n, because, for example, T can be a very long tree with depth of order n, but T prime can be a complete binary tree, which is completely balanced, and the depth of this tree would be a logarithm of n. And one can see that in the second tree, which is complete binary tree, we can find a path of at most size logarithm of n, or a multiple of that. So the kappa is not larger than a constant multiple of logarithm of n in this example. So the first one is easy. One can ask another question. Instead of considering all binary trees, we consider only balanced binary trees, which the one that I just described. We start from one vertex, we split it in two, and we split every vertex in two, and we go up to the fixed level in a balanced way. So the tree is fixed here, but we can number the leaves in different ways. It has been proved by Steele and another person that I have forgotten the name, that the minimum size of the largest common subtree is of order n to the 1/6 in this model. These are worst case scenarios. Now we are looking for results for random binary trees, which means that we pick the two trees T and T prime randomly, and we want to see how large is this kappa. More precisely, by random tree, I mean this. We let T of A be the set of all trees with leaf set A, which are finitely many trees under this isomorphism. Since the number of trees with leaf set A is finite, we can consider the uniform distribution on this set, which is equivalently picking one of the trees randomly and uniformly. So by a random binary tree, I mean a random element of T of A, and always assume random means uniformly random for simplicity. Now pick two trees, T0 and T prime 0, randomly and uniformly, and also independently from each other. The question is, what can we say about this kappa, or the expected value of kappa? Because this kappa is now random, because the trees are random. So the expected value of kappa is now a number, which is a function of n. So the question is, how does it grow as n goes to infinity? The conjecture is that this kappa itself as a random variable grows like z, which is a random variable, times n to the beta. This z does not depend on n. More explicitly, if we divide the left side by n to the beta, it converges weakly. This is the conjecture. But we are not even close to this conjecture, because we even cannot prove the existence of this exponent beta. This is the first step. Only some upper bounds and lower bounds for beta are obtained. The upper bound, there is an easy upper bound, which is of order n to the 1/2. This is proved by first moment method, counting all trees by counting arguments. So it's not very easy. There is a very recent result that improves the bound to 1/2 minus a very small number. It's I guess 10 to the -6 or even smaller, the bound that they have obtained. But at least it shows that the bound is not equal to 1/2. The exponent is not 1/2. I forgot to say that Steele and his co-authors have simulated the value of kappa as well for this model, and they have seen that it behaves roughly as n to the 1/2, but they conjectured it is n to the 1/2, but now this conjecture is disputed because they have proved that the bound is strictly less than this one. In this paper, we look for lower bounds. For lower bounds, basically we should construct a subtree of T0 and T prime 0, which is big. This way, if we construct a good common subtree, we can find a lower bound. The first bound was proved in the paper of Steele and his co-authors, which is the lower bound of order n to the 1/8. This one is recently improved by Aldous to a lower bound of order n to the 0.36, which I will explain in this talk. And I have improved this to n to the 0.44. More precisely, this is the more precise statement, that I defined some constant beta, which is by simulation between these two numbers. So the number beta will be defined by some equations. And I proved that for every beta prime less than beta, we have the expected value of kappa is of order at least n to the beta prime. So it is roughly, it means that what we are looking for is of order n to the beta, but not exactly. We should allow to reduce beta a little to prove this statement. So as I said, for lower bounds, we should construct a common subtree and prove that it is of order n to the something to obtain a lower bound. Now I will explain the method of Aldous, and then I will explain my contribution. First, I start with some facts observed, proved by Aldous. One is that if you have n leaves, we should have exactly n minus 2 branch points. And so the number of all edges is exactly 2n minus 3. This gives a nice combinatorial properties. For example, if we let Cn be the number of binary trees with n leaves, then Cn plus 1 is exactly 2n minus 3 times Cn. The reason is that assume you have a tree with leaf set 1 to n. To obtain a tree with n plus 1 leaves, it is enough to attach a new leaf to the middle of one of the edges. I don't have a pen to draw it here, but assume we have a tree with n leaves, which is a binary tree. If if we pick one of the edges and we attach a new leaf in the middle of this edge, we obtain a binary tree with n plus 1 leaves. And there are exactly 2n minus 3 ways to pick a leaf and do this procedure. And this is 1 to 2n minus 3 matching. So the reverse procedure is if we have a tree with n plus 1 leaves, it's enough to delete the last leaf. We obtain a tree with n leaves. So we obtain this identity. So this gives a recursion to compute Cn, which is the multiplication of odd numbers, which has a nice factorial formula. And by Stirling approximate, we can say something about it, which will be used later. Another lemma is that if we fix a subset of the leaves and we look at the induced subtree on B, And now this is a random tree with leaf set B, and the lemma says that this random tree is uniform. So the model is consistent in some way. This allows us to do induction and things like that. The proof is by the lemma in the previous slide. For example, if B is the subset 1 to n minus 1, we can show that every tree with leaf set B appears with probability 1 over Cn, and or we can compute the probability exactly. So it's using counting, we can compute the probability. I skip the exact proof here. There is also another simple fact which is very essential in the proof. So I will explain it, and I hope I can explain it very well. Explain it well because it's the basis of the next arguments. Assume that we have two trees, T0 and T prime 0. In the picture, I have only drawn one of the trees. Assume a B, which is a subset of the leaf sets, is a common subtree. Now pick 3 leaves in the common subtree, which is drawn by red dots here, and attach these 3 leaves by shortest path. We see that the shortest path intersects at a branch point. So these 3 leaves determine a unique branch point which separates the 3. And if we split the tree at this branch point, we obtain 3 branches. One branch contains V1, one branch contains V2, this one, and one branch contains V3. And more precisely, by A1, I mean the leaf set of this branch, not exactly this branch. The point of this this branching is that if you pick another vertex, for example, this one, which is in A1, so if we pick a vertex in A1, then the tree induced on the 4 vertices looks like this, which means that we have a star and we have attached V to this edge adjacent to V1. So if V is in A2, V should be attached to the middle of this edge and so on. This means that if V is in A1 and also V is in the common subtree, then in the other tree, it should also be in A prime 1, because we assume that these 4 vertices are in the common subtree. So the 4 vertices induce the same tree in the 2 trees. It means that if V is in A1, then it should be in A prime 1 as well, and conversely. This shows that all of the vertices in the common subtree should be included in this union, which is the union of AI intersection with A prime I. If there is a question here, I appreciate if you ask, because we are going to use this. This is essential in the talk. Okay, so I hope that I have explained well. But if there is any question, please feel free to stop me. So this is the simple fact, which is if we pick 3 points in the common subtree, then we can obtain this inclusion, which means that we can throw out everything that is not in this union. Now Aldous defines an algorithm with this simple fact. So recall that the input of the algorithm are two trees with leaf set 0 to n. Here there are n plus 1 leaves for convenience. And the trees are chosen randomly, but in the next parts of the algorithm, we have no randomness. Now, sorry, there is some randomness, but the algorithm makes sense for non-random trees as well. Now pick 3 labels, V1, V2, and V3 at random with a uniform distribution, and consider the branch point determined by these 3 leaves, call them B. Split the big tree at this branch point. It gives a partition A1, A2, A3 of the leaf set, and do the same for T prime. It gives us another partition, A prime 1, A prime 2, A prime 3. It's difficult to draw both of the trees together because it overlaps with T0, and the picture would be very bad. But in the picture, I have only shown the intersection of AI and A prime I in the light blue regions. It means that for looking for the common subtree, we can throw out everything that is outside these blue regions. When we throw out everything that is outside, we find two trees in the first branch, two trees. One is in the first tree and one is in the second tree. We call them R1 and R prime 1. This is on the first branch. Notice that the first branch, the leaf set is A1 intersected with A prime 1, but there is another leaf which is B here. B, I should have drawn it inside the region here. B was not a leaf, but when we split at B, B becomes a leaf in the first tree. So for each of these three regions, we have two binary trees, which is R1 and R prime 1, R2, R prime 2, R3, and R prime 3. Aldous' idea is that since we are looking for a common subtree, it's enough to construct a common subtree of R1 and R prime 1, which is in this branch, and a common subtree of R2 and R prime 2 here, and a common subtree of R3 and R prime 3 here, and glue them at B. Now we find a common subtree of the whole trees T0 and T prime 0. So this is the idea, and we do recursion for this one. So for constructing a common subtree of R1 and R prime 1, we use the same algorithm. We should pick 3 leaves at random. But notice that we have already picked one leaf, which is V1, and there is also a natural leaf, which is B. So we need to choose one more leaf in the next step, and we continue similarly. So this was the definition of the algorithm. Now it's time to analyze the algorithm to show that it produces a large subtree. So first, Aldous gives a heuristic analysis, and then the precise proof, which surprisingly uses the heuristic, but the heuristic itself is not precise. So the heuristic is not precise because Aldous assumes that the size of the output is exactly of order C times n to the beta. So if we assume that this convergence holds, then Aldous computes the value of beta as follows. First, normalize the sizes of the 3 branches, normalize by 1 over n so that their sum is equal to 1. Let's call them U1, U2, and U3. First, Aldous proves that these 3 numbers, which are random, converge in distribution to a given distribution, which is called Dirichlet distribution on the simplex. Then Aldous shows that conditioned on knowing the sizes of the 3 branches, then the leaf set of A1 is a random subset of the given size. By random here, I mean that A1 has a uniform distribution now among all of the ways that we can choose a subset of this given size. A1 has the uniform distribution. The same holds for A prime 1 as well. So A1 and A prime 1 are 2 random uniform subsets. And then Aldous proves that the intersection of these 2, which is random, is highly concentrated around its mean, its expectation. This is used in the computations. Another fact is that if we know the leaf set A1 and A prime 1, then R1 is the yellow tree in this branch, then R1 is also a uniform binary tree on the first branch. And also this R1 is independent of R prime 1. This is also proved by Aldous. And now this, since R1 and R prime are independent and uniform, we can go back to the first line. They should satisfy this first line, which means that the expected value of the output of the algorithm should be C times the number of vertices, which is here, to the beta. So we find this identity here. And notice that since the size is random, we add another expectation here. Now we find an identity. This one was the output of the algorithm. This one is the output of the first branch, the output of the second branch, and the output of the third branch. So we find this identity. We divide by n to the beta. So we obtain this identity. Now, since U1 has a known distribution, which is obtained from the digital distribution, Aldous computed the value of beta exactly, which is this one. So this is no proof right now because in the first step, we assumed the convergence, and then it was important here in this cancellation law. But surprisingly, this heuristic equation, which is this one, the second line, this is very important in the rigorous proof. Okay, the rigorous proof, first Aldous proves this convergence to the digital distribution, and then Aldous uses a martingale argument. He constructs a martingale in this splitting process, a sub-martingale in fact, and he uses the optional sampling theorem to prove the inequality. But in the improvement that I will explain, I have also simplified Aldous's method. Instead of the sub-martingale, it's enough to use a simple induction. So there is no martingale needed in my proof. Now I will explain how to improve this algorithm. Actually, the improvement is suggested by Aldous, but I have modified his suggestion. Aldous has suggested to split the trees at another branch point, which is almost in the middle of the tree. This I will explain what is the definition of this centroid, which is the point in the middle of the tree. And Aldous argues that it would probably give a better bound. The centroid is a branch point B such that the maximum of these three branches is bounded by n½ n/2. It can be shown that there is a unique branch point with this property, or if it is not unique, there are only two adjacent points in the middle which satisfy this one. The reason is that if we move the blue point from here to this one, then two of these large branches, for example, this one and this one, join and become another branch, and this branch will be very big. So this shows the uniqueness of the centroid, or in the worst case, there are two centroids which in the middle, we choose one of them randomly and we call it the centroid. And the rest of the algorithm is similar. We split at the centroid and continue similarly. But another argument is that since we split at the centroid, we should number these three branches 1, 2, and 3. To number them correctly, we sort them by size. Then it has more chance to throw out less number of vertices in the recursive algorithm, and this would probably give us a bigger tree. To analyze it heuristically, first Aldous proves the convergence of the normalized sizes. This has no problem. But in the second line, the identity that we obtain heuristically, there is a problem. Recall that this was the size of the output, and this was the output of the first branch, second branch, and third branch. But there is an inequality here because we have a condition in the next level of the algorithm. For example, in the first branch, we split it at the centroid. So the centroid is a special leaf in the first branch now. And this leaf, we should require that this leaf is included in the common subtree. So since we add a condition, this is this is not equal to the largest subtree without this this requirement. So this gives us an inequality here. So the reason is that we started with a tree such that no special leaf is selected, but in the next levels we have a special leaf. If we replace this inequality by an equality, there is no reason for that, but if we do this, we obtain the value of beta prime is 0.48. But now this one is an upper bound for the correct beta, but since beta should also be a lower bound for the problem, we have obtained an upper bound for a lower bound. So this has no mathematical value. So Aldous does this suggestion, but I couldn't analyze the asymptotics of the algorithm. This is what
the parameter of the Dirichlet distribution are minus half or plus half? And we are minus half.
Half. The previous model was plus half here.
Okay.
Here it is, but here is minus.
Okay.
But maybe you mean that Dirichlet distribution, the parameters should be strictly positive.
Yes.
This is true, but the point is that this distribution is not defined on the whole simplex. Recall that when we split at the centroid, each of the three arguments is less than 1/2. This is by the definition of the centroid here. Okay. So this Dirichlet distribution is not defined on the whole simplex, so it is still well defined. If we define it on the whole simplex, the integral would be infinite, so that's a problem. But if we restrict it to the subset of the simplex, it is okay. Okay, now I explain my contribution, which is improving Aldous's algorithm. So actually, I have modified Aldous's algorithm and then analyzed the modified algorithm. So let me say the idea of modification. Recall that if we start with a tree which has no special leaf, then if we split it at the centroid, we obtain 3 leaves, 3 branches, but the branches have 1 special leaf. So if we want to continue recursively, we should give an algorithm for trees with 1 special leaf as well. Now, I define another algorithm, which is given a tree with 1 special leaf. Again, split it at the centroid and split it in 3 branches. Recall that, note that one of these branches, which is this one, contains 2 special leaves now. One is the new centroid and one is the previous special leaf. So if we want to do recursion, we should give another algorithm for trees with 2 special leaves. Now assume from the beginning that we have 2 special leaves, which are shown by a star and bullet in this picture. Instead of cutting at the centroid, I will cut the tree at a vertex on this path, which is the shortest path between the 2 special leaves. So I choose almost middle of this path, but not exactly middle. It's the projection of the centroid on the path, so the shortest vertex to the centroid. I call it the semi-centroid. So I modify Aldous's algorithm by cutting at the semi-centroid in this case. And actually, we can argue that it is strictly better than cutting at the centroid. So it avoids the problems in theory, and also we can prove that it is strictly better. It gives a better result than splitting at the centroid. So here is the more formal algorithm. We give an algorithm. In fact, we give 3 algorithms. One is for trees with no special leaf. One is for trees with 1 special leaf, and one is trees with 2 special leaves. I call them T0, T1, and T2. T2, the index shows the number of special leaves here. And I say that they are type 0, type 1, and type 2. So construct an independent tree, which can be T prime 0, T prime 1, or T prime 2, similarly. And we define the value of kappa which is the size of the largest common subtree, but we have a condition here that the subtree should include the special leaves. So we have 3 values of kappa here. We can ask the same question: what is the growth of the expected value of kappa? We expect that they grow again like ci times n to the beta, but we will see that these ci's, the coefficients should be different. They cannot be equal. We will show in the next slide. But it's easy to show that by the argument that I will give later. One can show that the exponents are equal, but only the coefficients are different. So there is a C0, C1, and C2 in this equation that we expect to be true. So here is the definition of the algorithm. We construct a common subtree of Ti and T prime I for every I. For trees of type 0, we exactly use Aldous' algorithm. We consider the centroid split at the centroid, consider the trees Ri and R prime I on the branches, but we know that now Ri and R prime I have one special leaf. So when we want to go recursively, we use the algorithm for trees of type 1 in the next step. So the difference with Aldous' algorithm is this one. Now, another algorithm for trees of type 1. Again, we split at the centroid. We obtain 3 branches. We number the 3 branches in a way that the third one contains the special leaf. So we require that this leaf star is in A3. And for the other 2 branches, we can number them arbitrarily. So we sort them by size. If they have equal size, we choose the numbering randomly. Now we split at this point, we obtain 3 pairs of trees on the branches. We notice that R1 and R prime 1 are of type 1 because they have one special leaf, which is the centroid. R2 and R prime 2 are also of type 1 because in this branch we have also one special leaf. But R3 and R prime 3 are of type 2 because here we have 2 special leaves. So in the next step of the algorithm, to find a common subtree for the first 2 branches, we use the algorithm for type 1. For the third branch, we use the algorithm for type 2, which is in the next slide. If we are given trees of type 2, we split at the semi-centroid. I've already explained it, but I give the precise definition here. The semi-centroid is a vertex on the segment or on the path connecting the 2 branch points with this condition. The condition is that after splitting, the 2 branches should be less than n over 2. First, I should say that we choose the numberings such that A1 is the branch containing a star, A2 is the branch containing bullet, and the third one, we call it A3. So we require that these 2 branches are less than n half, but the third branch can be very big or very small. We have no control on it. Now we split at the centroid and we continue recursively. But the point is that in the next step, we do not need an algorithm for trees of type 3, for example, because each of these 3 branches are of type or 1. So actually we have, in the recursion, we only see trees of type 1 or 2. We do not see type 0 as well, unless the first step, only in the first step we have trees of type 0, but in the next step we see only type 1 and type 2. Now a heuristic analysis of the algorithm. Here we expect that the expected size of the output is Ci n to the beta for some Ci and beta. Consider the normalized sizes. I proved that the normalized sizes, which is V1, V2, and V3, converge to some explicit distribution, which is some Dirichlet distribution with other parameters. Now we obtain this equality. This is the size of the output for trees of type 1. This is the output of the first branch, which is also type 1, so there is C1 here. The second branch is of type 1, so there is C1. The third branch is of type 2, so there is C2 here. So it's different from the previous equations because there are C1 and C2 in the equation. If we divide by n to the beta and also divide by C1, and we call alpha to be C2 over C1, we obtain this identity. Note that this identity, there is only alpha and beta unknown. The distribution of V1, V2, and V3 is exactly known. So we have one equation with two parameters. We need another equation to solve it. The other equation is obtained for trees of type 2. Again, I show that the normalized sizes after splitting converge to some explicit distribution, and we obtain a similar identity. But note that there is C2 everywhere here, except the last one, because all of the trees of type 2 except the third branch, which is of type 1. So if we divide by C1 into the beta again, we obtain another equality. Now we have two equations in alpha and beta. Hopefully in alpha it is linear, so we can solve it in alpha. Now we have one equation in beta, which I use simulation because by monotonicity, we can use simulation easily to find the value of beta that satisfies this, and the value is the bound 0.44 that I have obtained. In this part of the paper, I have used simulation, but in the rest, there is no simulation. Actually, I have proved that for the value of beta satisfying this equation, we have the asymptotic result. Okay, now we want to prove this heuristic. Recall that this was only a heuristic equation. It was not yet proved. I will prove this by induction, but how should we prove by induction that something is of order n to the beta? At first, it's impossible to do induction for this, but if we change the statement of the theorem to a more quantitative way, we can use induction. So here is the more quantitative way of stating the result. The result is that consider alpha and beta, which are defined by the heuristic equations, and I prove that if we choose any beta prime less than beta, then there exists some delta positive such that for all n we have this inequality. So there is no order or omega here. It's an exact inequality, so we can use induction for this. I think I have not much time. How much time do you have to prove these arguments?
2 minutes, please.
How much?
2 minutes.
2 minutes?
Yes, please.
Okay, to prove this, first, I wanted to explain how we can prove convergence to the Dirichlet distribution, but this is by the same method of Aldous. So I just say the statement. For trees of type 1, they converge to Dirichlet with parameter +1/2, and -1/2 on a subset of the simplex. So the proof is by the combinatorial identities similarly to the argument of Aldous. And for trees of type 2, let me skip. For trees of type 2, we have a similar statement, but the parameters are -1/2, and +1/2. Now here is the idea of the induction. Let gamma of T1 and T prime 1 be the size of the output of the algorithm. It is not kappa because kappa was the largest common subtree, but we gave one algorithm, which we call the output gamma. The identity is that the output is the union of the output of the three branches. So we have this equality. Now, in the right-hand side, we can use the induction hypothesis because Ri and R prime I are independent and uniform. So if the induction hypothesis was true, we can use induction hypothesis for this term. And more precisely, we first condition on knowing the three pairs of leaf sets. Then after this conditioning, we have the independence property of Ri and R prime I. So by the induction hypothesis, the expected value of gamma is at least 1 or alpha times delta, the number of vertices to beta prime. Recall that this is exactly the statement of the theorem. Here, 1 or alpha times delta times n to the beta prime. Okay. Now we take expectation of both sides. Here we have expected value of gamma is at least 1 or alpha delta, the expected value of this value. Now this is complicated to compute exactly, but since the intersection here is concentrated around the mean, we can move beta prime out. Then this expectation is easy to compute using the Dirichlet distribution, which is shown here. In the limit, we obtain a lower bound with this Dirichlet distribution here. But for every epsilon, for large enough n, we have this inequality. Now, I explain the proof. First, I define alpha and beta. We fix beta prime less than beta. We should choose a delta such that we have the more quantitative statement. So I should define the delta now. First, recall that if beta prime was beta, these two terms were equal to 1 or alpha in the heuristic equations. Now, since beta prime is less than beta, this is strictly bigger than 1, and this one is bigger than alpha, so we can choose an epsilon satisfying this. And by the lemma, for this value of epsilon, we have, for large enough n, we find this inequality, which means that there exists a capital N such that for all n after that, we have this inequality. Now, if I want to use induction for smaller values of n, we do not have this lemma. So I cannot use this lemma if n is smaller than capital N. So I cheat and I choose delta very small so that for all small n, we already have the statement. Now to use induction, automatically in the n first steps of the induction are true. So in the n+1 level, I can use this equation and so on. So this is the idea of the proof, and everything will cancel out and complete the induction. So I skip the details. I just explain the argument. Okay, thank you very much.
Thank you. Thank you for you, Dr. Ali, for this nice talk. Are there some questions, please? Some questions? What is the relation between gamma and kappa? How we can found kappa from gamma? We have some control on gamma. How we can found the control about kappa?
Yes, here. We know that kappa is the output of the algorithm, which is less than kappa because the kappa is the largest common subtree, but for gamma we have constructed one common subtree. So this one is smaller than the largest. So we have this inequality.
Okay. So gamma is needed to obtain a lower bound of the expected value of kappa.
Yes. So the previous theorem we obtained a lower bound for gamma. So this automatically gives us a lower bound for kappa as well.
Okay. There is no relation between kappa and distance. Kappa is not a function of a distance between. You understand my question? We cannot construct a distance from kappa.
A distance?
Yes. Between two trees.
Yes, actually, the kappa of two trees is a measure of similarity of the two trees.
Yes.
Can't say that the distance is, say, n minus kappa, for example. The distance
yes. Okay.
Metric on the set of all trees or not.
Okay. And what do you mean by balanced binary tree? What is balanced binary tree?
By a balanced binary tree, which means that we start from one vertex, we split it in two. And for both, we split both of them in two. We have now 4 vertices.
Okay.
Instead of the 4 vertices by 2, we have now 8 vertices.
Okay. So we must have the deterministic tree and not random tree.
Yes, the tree here is not random. Only the labeling of the leaves is random.
Okay. And the value of beta, if I have well understand, is obtained heuristically and not mathematically. You understand? The value of beta, the bound of beta, we have no idea about the exact value of beta. We have just by simulation.
Actually, I have proved this theorem. Where is it? Here. I have proved that for the alpha and beta, which are obtained by the equation that we have this result. So,
but this result is based on some heuristic results.
No, the value of beta is defined by the heuristic results, but the rest of the argument does not use the heuristic.
Okay, but sorry, this can you go? Okay, this theorem. In this theorem, you suppose that the beta is given, but it is given by heuristic, and you prove your theorem.
So let me state it more precisely. Now, forget about the heuristics. Consider these two equations. Okay, these two equations determine uniquely a value of alpha and beta.
Mm-hmm.
So if we forget everything that I said about the heuristics, I just defined two equations here and define alpha and beta by these two equations. And for this value of alpha and beta, I proved the theorem.
Okay. And in your theorem 2022, can you go back to theorem 2022? Your theorem. Okay, 2022.
It was
in the beginning, I think, in the beginning of the slides. Yes.
Sorry.
Okay, here. For some constant beta between 0.55, 44, and so on, and for every beta prime less than beta prime must be between these two bounds or not?
No, beta can be anything less than
anything but less than beta. Okay. Okay. Yes.
I should say that for the value of beta defined by the equation that we explained it in the for that value of beta we have this.
Okay. And no results about the maximum of kappa, about the expected value of maximum of kappa. There is no results. I think it will be hard.
Kappa itself is the maximum of.
Okay, maximum. Yes. Sorry. Yes. The maximum of size of sub-tree of sub-common tree between T and T prime. Okay. Are there other questions, please? Are there some questions? If no other questions, we have to thank again Dr. Ali for this nice talk.
Thank you.
And see you next after 2 weeks. Thank you, Ali. Thank you. Nice to meet you. Bye.
Bye.
Bye.